Hi friends, this is Visal Nadapra, Department of Mechanical Engineering, Dr. Subhash Technical Campus, Junagadh. Welcomes you in a lecture series of fluid mechanics, in which we were discussing about laminar flow. In which in previous lecture we had discussed about the characteristic of laminar flow, difference between laminar and turbulent flow, then Reynolds experiment. After performance of the experiment, we had seen three different results or three different observations, and how we can learn how we can differentiate laminar flow, transient flow, and turbulent flow just by observation. And lastly, we had seen the flow of viscous fluid in the circular pipe, in which we had derived the equation of velocity and also seen the velocity distribution along the cross section of the pipe and shear stress distribution too. After that, we had derived the equation of loss of head in the circular pipe, which is nothing but the Hazen-Poiseuille formula. Today we are going to discuss about the flow of viscous fluid between two parallel plates, and we have derived the same equation just as Hazen-Poiseuille formula of velocity distribution, shear stress distribution, and head loss between two parallel plates. So let's begin. This is two parallel plates, both are fixed, so there is no velocity, and direction of flow is given from left to right direction. Let's consider a very small element with the cross section area. Here not is cross section area. Here the dimension is delta y, and the uh, perpendicular dimension to the slide is unity. So the area is delta y times 1. So it is ultimately only a delta y. And consider the length of this elemental area is delta x, which is denoted here. And distance of this elemental area, it is y from the bottom plate, parallel bottom plate. So let's consider the distance we will measure. It is with reference to the bottom plate in this direction. Say this is the y. So and the distance between these two parallel plate is small t. Say it is the gap between these two parallel plate, and viscous fluid is flowing in this direction from left to right direction. Now, for the analysis purpose, as we have considered a small elemental volume, so first let's consider the amount of, or we can say number of forces acting on this elemental area. Here we will consider the two type of forces as in the previous theory. First one is the pressure force, and another is the shear stress force. So pressure force, as per the definition, it is the pressure, intensity of pressure times the area. So here we have noted this elemental area, surface area is ABCD. Actually, it is not an area, but it is volume. But for the sake of simplicity, we have taken the distance perpendicular to the slide is unity. So we can say it is also a area. But keep in mind, it is not an area; it is an volume. So let's consider the forces. First, a pressure force which always act on the perpendicular direction to the surface, and at on the side AB, let's consider the intensity of pressure is small p, and thus the pressure force acting on the side AB is pressure intensity time intensity of pressure times the area. So P into delta Y into 1. The same way, pressure acting on the side CD, it is again perpendicular to the distance, perpendicular to the side or perpendicular to the surface, and it is in opposite direction because it have a always tendency to act perpendicular to the surface. But here keep in mind, we considered that pressure intensity of pressure is something different. It may be increase or maybe decrease, that we cannot say at the time. So for just consider the del P by del X is the rate of change of pressure in the X direction, as we have taken many times. So for the difference of pressure between side AB and side CD is here. If here it is the P, then here it is the P plus del P by del X times delta X. So this is the intensity of pressure on the side CD. So this much parameter or this much increment, let's suppose, will be done on the between side AB to side CD, and thus the pressure force acting on the CD is intensity of pressure times the area, which is nothing but the delta Y into 1. So here we consider two pressure forces on the side AB on the side CD. Now let's consider another force, which is the shear stress force. So for that, consider the shear stress acting on the side BC and side AD. Here the shear stress is, let's suppose it is a tau, and thus the velocity, the force or shear force on this side BC is shear stress times the area, and the area is again delta x, which is nothing but the length times the thickness, which is perpendicular to the slide. So here we can say the area is delta x times 1. So the total pressure shear stress force acting on the side BC is tau times delta x. So this is the pressure force on the bottom side. Now if we consider the top side, here again we have to consider the shear stress distribution or the shear stress increment, which is nothing but the tau plus del tau by del y. Here del tau by del y, it is the shear stress, rate of shear stress with respect to y direction. Here in vertical direction we have considered as a y. So in this case, del tau by del y is nothing but the rate of change of shear stress with respect to y direction. So the shear stress is tau plus del tau by del y into delta y. So if this is the intensity of shear stress or the shear stress, then shear stress force is the stress times the area, which is delta x times 1. So this is the total pressure, total shear stress on this side AD. But one thing you have to keep in mind, which is the direction of this shear stress. In the BC, it is opposite to the direction of the shear stress, where on the AD, it is parallel to the or in the same direction of the flow, which is just because of the velocity difference between two layer or the layer adjacent to this considered elemental volume. Just because on the side BC and the just adjacent layer of the fluid which is flowing just near to the side BC have a velocity less than the velocity of less than the fluid velocity, less than the velocity which occur or which produced on the side BC, whereas in the AD it is something opposite, because the layer which is just adjacent to the side AD have a higher velocity than this AD. So this is the reason for different direction of these both shear forces. So here we have considered the two type of forces, pressure forces and two types of shear forces on the different side. Now let's consider this is in equilibrium condition, and the net force acting on the side ABCD or volume ABCD is equal to 0. Then again another consideration, left to right, consider left to right direction, it will be a positive for horizontal forces, and upward to upward direction will be a positive for vertical forces here. So after considering the equilibrium condition, we get the equation like this, P delta Y into 1, which is from left to right direction, so it is positive, and on the opposite side, this is the uh, in opposite direction, so it have a negative sign here. The same way here for the shear stress also, upward direction force, upward direction force here, it is not it is not actually upward direction, but it is horizontal direction, but it come opposite to the flow, so it is negative, and this is going with the flow, so it will be a positive. And after considering after simplification, we get the relation del P by del X equal to delta by del Y. So by thus we can say del P by del X, say it is the rate of change of pressure, it equal to the rate of change of shear stress in vertical direction. Let's say it is an equation number 1. Now let's derive the equation for the velocity, or simply a velocity distribution. For that we have to take Newton's law of viscosity, which is tau equal to mu into du by dy. Put the value of tau in the above equation, or equation number 1. We get the equation del P by del X equal to del by del Y of mu into du by dy. Now mu is the constant, so it will be come outside of the sign of differentiation, and you have get the second derivative delta u by del 2u by del y square. So it is the second derivative uh, of with respect to y. So to get the equation of velocity, let's make capital U of the equation. Then it will be a del 2u by del y square equal to 1 by dynamic viscosity times the del p by del x. This is nothing but the rate of change of pressure. To get the value of u, we must have to integrate this equation. So integrating the above equation, we get the value by this the first integration, and this is the without limit. So unlimited integration, so we have to consider one constant of integration, which is c1. But here again, we get the velocity in terms of del u by dy is in differentiation form. So to get the exact value of velocity, we have to again integrate this equation. And after integration this equation, we get the value of u like 1 by mu times del p by del x times y square by 2 plus c1y. Because c1 times 1, and the integration of 1 is y plus c2. It is nothing but the constant of integration when we take the integration without limit. So we get this equation of velocity distribution. But here we got the two constant by free of cost. Buy one get two free like this. So to get value of c1 and c2, we must have to apply the boundary condition for between two parallel plates. So in this case, it will be something like this. Say this is the two parallel plates, and at this point, at this boundary, and at this boundary, we will apply the boundary condition. And in this case, we will consider two variable u and y. Y we have considered in upward direction, so value of y will be 0 here, and in this case, or the top on the top surface or the top parallel plate, we get the value of y equal to distance between these two plates that we have considered t already. So this is the value of y at two boundary, and for that case here, is this the viscous flow, and when the viscous flow is flowing between in contact with any fixed surface, then the adjacent layer to the fixed surface always have a velocity equal to 0. So in this case, velocity equal to 0 here also, and here also u equal to 0. So by applying condition, first condition at y equal to 0, at u equal to 0, so this is the condition here at this point. So at this point, value of y is equal to 0, and as it is in contact with the solid surface or the fixed surface, it have a velocity u equal to 0. So we get the value by putting this value u equal to 0 here and y equal to 0 here. We get the value of c2 equal to 0. Then another condition, which is on the top surface at y equal to t. So the dimension of y equal to t here, and again velocity will be 0 because it is in contact with the fixed surface or the fixed plate. By putting these two value and the value of c2, if we put the value of c2, it will be 0. Then y equal to t, put the y equal to t here, and u equal to 0 here. Then we get the equation c1 equal to minus 1 by mu del p by del x into t square by 2t. T will be cancel out, and the final equation or the final value of c1 will be a minus 1 upon twice mu del p by del x into t. So we get the two value or the two value of two constant c1 and c2 by putting this value both here in the equation of u. We get the equation like this: u equal to minus 1 upon twice mu del p by del x into ty minus y square. It is nothing but the just a simple simplification. So this is the velocity distribution between velocity distribution of the viscous fluid between two parallel plates, in which u is the velocity, 1 upon twice mu it is constant, mu it is the dynamic viscosity, which is always constant for a particular constant temperature. Del p by del x is the rate of change of pressure in the x direction, which is also we can consider as a constant value. So here u is vary with respect to y with relation or with the parabolic relation. So we get u or the velocity distribution along the pipe like this. So here it is the velocity distribution, and we get the parabolic relation. Here velocity is 0 on both at both the surfaces, and at the center we get the maximum velocity. We will derive the velocity, maximum velocity in a couple of minutes. So let's start the ratio of maximum velocity to the average velocity. First, we will derive the equation of maximum velocity and then average velocity, and then we will take the ratio of both this. So for maximum velocity, put the value in the previous equation of velocity distribution, and put the value where we get the maximum velocity. It is nothing but the center distance between two parallel plates. So put the value of y here. So we measure the y from the bottom surface or the bottom plate, and here the value of y equal to t by 2, or half of the total distance. So by putting this value, and we get the maximum velocity. So instead of u, it is a u maximum, and instead of y, put the t by 2. So we get the equation u max equal to minus 1 by twice mu del p by del x into t into ty. Instead of y, it is t by 2 minus y square. So again, t by 2 whole square. By just simple simplification, we get the value of u maximum is equal to minus 1 by 8 mu times del p by del x times t square. So thus we get the value of u maximum. Now let's calculate the average velocity. To get the average velocity, again we have to consider a very small strip, as we have considered in the previous theory, and we will first derive the equation of flow from that small strip, and for the getting to get the value of discharge or from the whole cross section area, we will integrate that equation. So first consider del q. It is nothing but the uh, discharge from a very small area, which is equal to velocity at a distance y times area of the strip. Area of the strip, again we have considered del y into del y times 1, because 1 is the perpendicular distance to the board, and dy is the cross section area of this cross section dimension, or the vertical dimension of this element considered. And the velocity equation we have previously derived, which is minus 1 upon 12 mu del p by del x into ty minus y square times dy times 1. So this is the discharge through a very small elemental volume we have considered. To get the total discharge, we will integrate this equation. So integrating this equation, limit is time y equal to 0 to y equal to t. So by this way we can get the discharge of between two parallel plates. So by integrating this, first we will take the common or the constant value out of the integration sign, and integrating t into y square by 2 minus y cube by 3. So by this way we get the integration, and after that putting the value of this limit, first upper limit minus lower limit, and thus we get the relation like this. So it is minus 1 upon times mu del p by del x into t cube by 6, and after removing and multiplication of 6 and 2, we get the relation minus 1 upon 12 mu del p by del x into twice cube. But this is the value of q only. We require average velocity u bar. So to get the average velocity of q bar, we must have to divide this discharge with the cross section area, or the area between two parallel plates. So this is nothing but the height into thickness perpendicular to the slide. So here height is t, which is nothing but the distance between two parallel plates times the thickness that already we have considered 1. So q is 1 by 12 mu times del p by del x into t cube divided by t into 1. It is the cross section area between two parallel plate. So after simplification, we get the value of u bar, which is equal to minus 1 upon 12 mu del p by del x into t square. After getting the equation of u max, which is here, and u bar, which is the average velocity and which is given here, we will take the ratio of u max by u bar, then common parameter will be cancelled out, 1 upon mu, del p by del x, t square, t square here and t square here. So 1 upon 8 mu, negative will be also cancelled out, so the final ratio will be positive. And 1 upon 8 mu is also common, and in both the cases it in uh, denominator, so it will also cancel out, so it will be 1 upon 8 divided by 1 upon 12, so ultimately it is 12 by 8 and it is 3 by 2. Thus we get the ratio of u max by u bar when the viscous fluid is flowing between two parallel fixed plate. It is equal to 3 by 2, which is very important ratio while deriving the while solution of the problem between two parallel plates. So let's consider the drop of pressure head for a given length of the pipe. Here, let's consider, sorry, not pipe here, but between two parallel plate. So let's consider two parallel plate here, and consider section 1 here, which have a distance from the starting point or the reference point of x1, and section 2 have a distance from reference point is x2, and the distance between these two is again L, which is nothing but the x2 minus x1. To get the value, we must have to start with the average velocity u bar equal to minus 1 upon del mu del p by del x into twice t square. But here we required the drop of pressure, so make the term pressure as a capital. So del p by del x equal to minus 12 mu u bar upon t square. To get the pressure difference, we must have to integrate this equation between section 1 and section 2. So integrating the above equation between two limits 1 and 2 to 1, dp is equal to 1 to 2 minus 12 mu u bar by t square into dx. So here p1 minus p2 is equal to minus 12 mu u bar upon t square into x1 minus x2. Here x1 minus x2 is minus L, so minus minus will be plus. So 12 mu u bar upon t square is equal to x2 minus x1, and we get the equation of difference of intensity of pressure is 12 mu u bar L upon t square. But this is the pressure difference, but we are much more interested in head loss instead of pressure difference. So let's derive the equation of head loss. To get the head loss, divide both the divide the equation on both the side by rho g, or simply a weight density. So we get the equation hf, say head loss between section 1 and 2, equal to P1 minus P2 by rho g equal to 12 mu u bar L upon gt square. So this is the most important equation while deriving the pressure head loss of the viscous fluid between two parallel plates. Now let's consider shear stress distribution. Here we have seen velocity distribution in the previously, but we did not derive any shear stress distribution or the equation of shear stress distribution between two parallel plates. So let's derive it. For that, again, tau equal to mu into du by dy. In this equation, put the value of u, or the velocity distribution, what we have derived earlier. So tau equal to mu into du by dy, mu times del u by del y of all the equation of velocity distribution between two parallel plates, which is minus 1 upon twice mu del p by del x into ty minus y square. By just doing a simple partial differentiation, we get the equation of shear stress distribution along the along the whole cross section area between two parallel plates, which is tau equal to 1 upon twice mu 1 upon twice del p by del x into t minus 2y. So this is the governing equation, or you can say shear stress distribution between two parallel plates when the viscous fluid is flowing uh, between two plates. So from this equation, we can conclude that here the 1 by 2 is constant, del p by del x is rate of change of pressure with respect to x direction. We can take is also a constant, t is the physical dimension, which is the distance between sorry, distance between two parallel plates. So we can say tau is directly proportional to y, and thus these have a linear relation between tau and y. So here we can say if y is increases, When y is increases, the value of t will decreases because here the negative sign is here. So as the y increases, the value of tau is decreases and it will become 0 at this point or center of the pipe when we put y equal to t by 2. So in this case tau will be 0, and again when the value of y is increases greater than t by 2, then again value of tau is increases, and thus we can say shear stress distribution between two parallel plates when the viscous fluid is flowing is a linear relation. So that is all for friend today. We have discussed today about the flow between viscous flow between two parallel plates which is fixed in condition. There is a no movement between plate. For that we have derived the velocity distribution and shear stress distribution and see the graphical relation or the graphical representation of the velocity distribution as well as shear stress distribution. Okay, thank you friends.